Okay, so for the first in-class exercise, we're sizing that flow equalization basin. You just, in the first two columns, are typing in the data that you've got, the time and the inflow. And so this is an inflow rate. You're going to need to calculate the inflow amount during each period. And so if you know what the rate is, and you know the duration of the period is 2 hours times 3,600 seconds per hour, then the way to get from here to here is you're just multiplying the flow rate by the duration, which is 7,200 seconds. So then you get, this is how much came in between 2 and 4, this much came in. Between 4 and 6, this much came in, and so on. The outflow is constant. That's given in the problem statement. It's always 0.2 cubic meters per second, and so you do the same thing here. Outflow amount during that increment. And so it's 0.2 cubic meters per second times 7,200 seconds, and then it gives you the flow rate out. Now, the water volume at the start of the period, this is where it gets a little bit tricky, because this is the starting amount, the 4,000 cubic meters. You just are given that it's 4 meters deep, and if you get the cross-sectional area, you'll find it's 1,000 square meters is the cross-sectional area. And so then this is saying, how much water is there at this time? Well, you have to look at how much there used to be versus how much came in and how much went out. And so you're actually, in this cell, you're saying it was 4,000 and 1440 came out at the same time as 193 came in. So it's this plus that minus that to give you the solution. And then the depth, you're just dividing by the cross-sectional area. So I think many of you were on that track already, but I just wanted to confirm in your minds that you're headed in the right direction in applying this mass balance principle. So I'm going to blank the screen out again so you can get back to your spreadsheet as you were doing it. We are talking about kinetics in this next one, and there's two different chemical reactions happening in two different tanks. And using a graphical approach, we want to find out what is the reaction order of these chemical reactions. And reaction order is something that has to do with the rate of the reaction and its dependency on the concentration that's there. And so an example of what this should look like is if we graph the data and we have time on this axis and concentration here, and we get a linear trend like that, then that would be zero order. Okay? If you graph the information and you have time on the x-axis, and on the y-axis you have the negative logarithm of C naught, of C versus C naught, and then it ends up being linear, then you've got first order. And then finally, if you graph the data and have time versus 1 over C and observe a linear trend, then that is second order. Yeah, this is linear, but the reason why it's linear is we took the data, and on this vertical axis, what we're plotting, we have a table of data that shows, you know, here's our data, and it says time and then concentration. And so we have data that's saying, you know, 0, 10, 20, 40, etc. And then concentration that's like 90, 72, 57, and etc. And so you can determine the reaction rate order by plotting it. There's different ways to do it, but one is to plot the data. And so you'd have time versus C. Or you'll have another column where you're going to say the negative natural log of C minus C naught. And C naught just means the initial concentration. And so here is our C naught. And so for each one of these, you'd have some value that you've calculated for the concentration at that particular time divided by C naught. Take the logarithm of it and then the negative. And so you go through, and then this column is what you would graph on the vertical axis to see if it's first order. And you can have both the equation y equals mx plus b and the r squared value. And so whichever one of these has the highest r squared value is the one that's closest to linear. And so you'd also have a column where you're having 1 divided by C, whatever the concentration is. And then that's what you'd graph on the vertical axis to see how well it matches up with linear behavior. Okay, so same thing. You can work with your partner, type in the data to another tab. Maybe you can see I've created a second tab down here called kinetics. Create another tab, type in the data, and then do this natural log column, do the 1 over C column, and then graph it to see. You're going to have 2 different sets of graphs. You're going to have 3 graphs for reaction 1, and then 3 different graphs for reaction 2, trying to observe in what cases is it linear. By the way, if you feel like you need to take a break, step out and use the restroom or get a drink of water, that's fine. Feel free to do that. We'll usually take like an actual pause in the action about halfway through the class period, sometimes between 6:30 and 7. But you know, when we're in the middle of an in-class exercise, you can just always step out and take a break if you need to. Okay, here's that first peek at the solution I put together to see if you're headed on the right track. So we've got reaction 1 separate from reaction 2. We have to consider them separately. We can't do it at the same time. So you're given the concentration, then you calculate the logarithm of the concentration at any particular time divided by the initial concentration. So you can see I'm anchoring up here to the initial concentration. And then in this third column, it's 1 divided by whatever the concentration happens to be at that particular time. And so you end up with 3 graphs. The 0 order graph is where I'm graphing these 2 columns. The first order graph is where I'm graphing time versus negative natural logarithm of the ratio. And then second order is 1 divided by C on the vertical axis. And you get an r squared for all 3 of them. And one of them has a really nice r squared of 1.0. So that's a perfect match. So we know that this first reaction is first order. So that's the direction I hope you're headed in, is just setting up the data and then doing the calculations. On this one, it's hard to see the K value for that second order reaction because the default formatting is, I think, general. And so all you see is 0.0008, and that's not very much precision. And so what you may consider doing is right-click on the label and format the trendline label. Instead of general, change it to scientific. And then you'll be able to see what it actually is, and it's 7.66 times 10 to the minus 4th. So that's just a way to see more of the digits. You could have also left it as a numeric and then increased the number of decimal places that it's showing, but scientific's probably the easiest way to go for that one. On this last one, we've got a completely mixed flow reactor. Sometimes it's also called a continuously stirred tank reactor. The flow coming in is 90. The flow going out, we want it to be 0.05% of 90 milligrams per liter, which is where this 4.5 milligrams per liter comes from once I start substituting things. It's basically just rearranging the equation to solve for the flow rate. In the book, it refers to V divided by Q as the residence time. And what this means is when water comes into the reactor, the average amount of time that a particle will spend spinning around inside of there before it gets kicked out. So if you have volume divided by a flow rate, then that's going to give you units of time. And so it's how many minutes it goes in there. So in our case, we know the volume of the reactor because it's given that this is a 500-liter reactor once we do the substitutions. But just rearranging to solve for the unknown flow rate, if we have a higher flow rate than this, if you go faster than 0.6 liters per minute, the problem with that is that the particles aren't going to spend long enough inside the reactor. You know, this reaction is occurring over time, and so if you increase the flow rate, then the particles aren't inside the reactor long enough, and they'll come out with a concentration that's higher than the 4.5 milligrams per liter that we're hoping for. And so it won't hit that 95% efficiency target if the flow rate's too high. If you reduce the flow rate, then it's just going to have more removal. Then actually the concentration would go lower than 4.5 milligrams per liter. So any questions on that last part? Okay. So you don't actually need to submit anything for this in-class exercise. What I'll do is I'll enter the grades online. I'm going to be using MU Online for the grade book. So anytime you want, you can just log into MU Online and see what your course average is. I'll have it set up so that it's always calculating an up-to-date grade for you. And you'll notice a column for in-class exercise 1, and it's just awarded on the basis basically of effort most weeks. It's just, you know, if you gave it an honest try, then I'll give you the full credit for the in-class exercise. All right. Well, now we are going to move on to the lecture portion of the evening. I've got some handouts for you. Here we go. You're welcome to sit wherever you like during the lecture. I'd asked you to move around a little bit to move into some pairs, but if you want to move back to where you were originally, that's okay. Here you go. Doesn't matter to me. Probably doesn't matter to you. Everybody have a copy of the notes? You don't have to print them, no. I'll give them to you every week. All right. So just a refresher of some announcements. Now you could look this same information off of the schedule I gave you. You know, the last page of the syllabus had that schedule that showed homework number 1 is due next week and that the presentation is due in 2 weeks. So you've got both of those things and can start working on them after tonight. So we've gone over the syllabus. We did in-class exercise 1, which the purpose of that was to review some of the fundamental concepts that are in the first chapter of the book. What we're going to do now is just do an overview of the characteristics of wastewater, an overview of the treatment system, basically that top-level view before we get into any one subject in too much detail. We'll talk about why biological treatment is used for wastewater, and for that matter, why we even bother treating wastewater before it's discharged. Because in some places they don't. So think about what is the utility of water. You know, what do we actually do with it? We drink water, you can boat on it, recreation, fishing. You know, those are some of the answers when I ask students in my introductory environmental engineering courses that I've taught in the past, what is the use of water? Those are some of the answers that I'll get. But one of the most important ways that we use water, and the greatest quantity that we use water, is just for moving waste around. If you look at how, you know, what's the per capita water use in the United States? You know, how many gallons per person per day, or liters per person per day, if you think in rational terms. It's about 300 to 400 liters per person per day in the United States, depending on where you live. You know, if you're in the western United States, the water use is a little bit higher than here because in many places they're irrigating lawns. So, you know, if I'm only drinking maybe a liter of water per day on a thirsty day, if I'm drinking a liter of water, Where is the other 399 liters of water? What is that being used for? It's being used to transport waste. The waste that accumulates on my clothing when I spill salad dressing on my shirt, I got to use a lot of water to transport it off my shirt and away. When you take a shower, you're using water to transport waste. Washing dishes, most of the ways that we use water in a residential setting is for transporting waste. And so that's why wastewater treatment exists, is because we're using water to transport waste, and before we put it back into the environment, we have to concentrate that waste so that it doesn't cause unintended or undesirable consequences when it gets back into the environment. So here's kind of an illustration of water being used in one of its moving waste around ways. A guy's washing a car. He's got the black socks and sandals going, so he's rocking that. He's got a sweet ride. And think about, if you're washing a car, what sort of waste is going to get into that water? You know, obviously if you're washing dishes, food waste will be into the water. If you're washing clothing, detergents and oils. What about when you wash a vehicle? You know, what is the water that you wash a car with picking up as you go through that cleaning process? Well, it may be salt in the winter. You know, if your roads have salt on them to try and bring the melting point of ice down to make it less slippery, well, that salt gets on your car, and so when you wash your car off, suddenly there's salt, and salt can have an undesirable effect on aquatic life, and so somehow we have to get rid of those dissolved solids. Here's a list of typical contaminants for wastewater. We'll talk about each of these in a lot of detail through the semester, but just briefly, suspended solids are those solids that aren't dissolved in the water, but it may be clay particles. And when you look at the Ohio River, the reason why it's brown, it's not brown because brown food coloring was added to the river. It's not brown because, you know, it's toilet waste that's going into the water. It's suspended clays. And you'll notice on when it's really heavy rainfall, and there's a flash flood, the smaller creeks that run adjacent to the roadways here in West Virginia look like it's chocolate, like a river of chocolate. It looks like Willy Wonka almost, but it's not. It's just clay. And the reason why it's so chocolatey looking is because when there's heavy rain, it suspends a lot of clay particles and it just starts scouring the bank, scouring the stream. So that's suspended solids is mostly clay, is what we're dealing with. One of the contaminants we'll talk about in more detail today is VOD, but there can also be germs, pathogens, bacteria, viruses, cryptosporidium, spores, all sorts of nasty stuff that we don't necessarily want people to be exposed to if we're going to discharge the waste upstream of where people are using the water for recreation. So if people are water skiing or fishing, then you'd want to be careful about the pathogens that you're discharging into those sorts of recreational areas. Dissolved solids will include salts, like that's used for defreezing the road. Heavy metals might be just atmospheric lead and mercury that settle out of the atmosphere and onto the road, and when it rains, then all of a sudden those heavy metals get into the water. And it can also be nutrients like phosphorus and nitrogen that are added to fields for enhancing agricultural production, but then those nutrients get into the water and they're pollutants because we want plants on land to grow, but we don't want to stimulate the growth of plants inside of water, like algae, cattails, and problematic weeds that will grow into channels. Those actually, we don't want to be stimulating their growth by adding nutrients. And so when a farmer is adding a lot of phosphorus and nitrogen to a field, but then there's runoff, then suddenly what was good for the plants becomes negative for the environment downstream. Priority organic pollutants is a class of pollutants that include things like pesticides or dry cleaning fluid, trichloroethylene, just any sort of organic constituent like maybe gasoline or benzene that's regulated and shouldn't be in the water. So Of these, the most common pollutants that are being removed from a wastewater treatment plant are the top 3. And then the rest of these are considered maybe secondary pollutants. And there's an episode of South Park where they're crawling around in the sewer. And anytime I see that episode, it sort of reminds me of the central importance of water for even the silliest plot line like South Park. All right, so of these, a lot of these it's obvious what it is. But the most obscure among these is VOD. It's something that I have to explain a couple of times to undergraduate students the first time I'm exposing them to VOD. In many cases, maybe you've already heard about VOD, but let's just review what it is. It stands for biochemical oxygen demand. But to illustrate what is VOD, the easiest way I can think of to illustrate what this pollutant is to think about sugar cubes. Now, sugar cubes aren't in and of themselves toxic. They don't hurt your body. Well, sort of. If you eat too much, you get diabetes. But one sugar cube is not going to kill you. And if you throw one sugar cube into the river, it's not going to cause any harm. So it's not toxic, but it can be a pollutant. And the reason why sugar can be a pollutant is think about what is the unintended consequence of putting food like this. We call it a substrate. If you put a substrate into the environment, what is it going to do? So if we empty bags and bags of sugar into a river, then the microorganisms are going to love that. There's just naturally bacteria in the water. They live there even when we're not discharging our waste to the water. There's all sorts of environmentally present bacteria. And when you add sugar to the stream, all of a sudden you've given them a food supply. They multiply, reproduce, and so the population of microorganisms is going to skyrocket because you added that sugar. And so their cellular respiration increases, they reproduce, and in addition to eating the sugar, they also consume oxygen, just like we do. When you give me a hamburger, I eat the hamburger, I drink water, but I'm also breathing. And so the bacteria that's in the water, when they're breathing, they're not breathing atmospheric oxygen, but they're breathing dissolved oxygen. And that's a problem because as they continue to breathe more oxygen by consuming the dissolved oxygen, then the concentration of dissolved oxygen in the water will decrease, and there's other things that need oxygen besides these bacteria. The fish need oxygen. There can be aquatic plants that need to have oxygen. But basically, the bottom line is that this VOD is a way of measuring what is going to be the impact on dissolved oxygen when you add an organic pollutant into a river. So if you pour in 1 pound of sugar, the question is, how much oxygen is going to be needed to break down that sugar? And so it's not just sugar. It can also be wastewater. You think, well, we wouldn't eat wastewater, but bacteria would. They're not picky. They'll eat wastewater. There's VOD in wastewater, and those bugs will eat it. And as they eat it, they also need oxygen. And so they start depleting the dissolved oxygen, and that is the pollutant. It's not necessarily the dissolved organic material that's the pollutant. It's the consequence of adding that dissolved organic material to the stream. So there's a way to test it before you discharge wastewater. It's called a VOD Bottle Test. And here the subscript 5, a VOD 5 test, basically means you put some wastewater into a bottle for 5 days and you just measure what happens. You find out what is happening with the dissolved oxygen over time. And here you can see there's many different bottles, and maybe they did that because they have samples from different days. Sometimes they have to dilute the waste because they don't know at the beginning of the test how much VOD is there. And so it wouldn't be full of wastewater. It would be maybe 297 milliliters of water and only 3 milliliters of wastewater, because the wastewater has so much VOD in it, it could use up all of the oxygen in the water, and then your test stops prematurely if you've used up all of the oxygen. You only want the dissolved oxygen to go down 2 or 3 or 4 milligrams per liter during the test. At the starting level, the maximum amount of oxygen that you can have in water is a function of temperature. Very cold water has about 14, 15 milligrams per liter of dissolved oxygen. But the warmer the water is, the solubility of dissolved oxygen decreases. And so at room temperature, this may have around 12 milligrams per liter to begin with. And then during the 5 days, this machine is measuring the air pressure in the tube. And that air pressure is an indicator of how much oxygen remains inside of the dissolved, how much dissolved oxygen remains in solution. So that's a VOD bottle test. When all of the VOD is used up, that's what we classify the ultimate VOD demand. You know, this first one, we were just talking about how much demand for oxygen is there during a 5-day period. But the bacteria are very resourceful. They'll break down every little molecule of energy that they can. And so it's not just the 5-day VOD that you have to be aware of, but the ultimate VOD, ultimate oxygen demand, L naught, is when all of the biochemical oxygen demand has been exerted, what is the amount of oxygen required to do that. And so here's a diagram that's just showing over time on one of the curves how much of the demand remains, and this is how much demand has been exerted. And so you can see that they're the inverse of one another. At the beginning, there's a lot of demand at time 0. When all of the waste is just barely been poured into the river, then you've got a lot of work to do. There's going to be a lot of oxygen consumed to break down that energy source. But over time, you've broken down almost all, and finally you get to some point in this illustration, they're saying it may take as long as 30 days before all of the waste is broken down and all of the oxygen demand has exerted itself. So that's what ultimate VOD is. And we have equations that relates the oxygen demand at a certain time to the ultimate demand. And you can see that there's 2 equations listed here. One, that they're both logarithmic. This top one is logarithmic base E, so natural log, and this bottom one is base 10 units, so it's log instead of natural log. And the relationship between the K values is shown there on the screen. The little k goes along with natural log, and it is 2.303 times the big K. The K is the rate constant, similar to what we did in the in-class exercise today. It relates the kinetics of how quickly the bacteria are breaking down the energy source and consuming oxygen. So let's just do a little example here, just some calculations. We've got a graph that shows us what is happening during a test, and at the end of 8 days, an 8-day test, we found out that this wastewater consumed 180 milligrams of oxygen for every liter of wastewater that was discharged. Now, you remember I was saying earlier that typically water will have maybe around 10 to 12 milligrams per liter of oxygen. And so, you know, this is saying that for every liter of wastewater you're pouring into the river, you need to have 180 milligrams per liter of oxygen available. And so you're going to have to dilute this in order to satisfy that demand for oxygen. But the question is really asking, if you know that at the very end of the test, ultimately there will be 212 milligrams per liter, then what does that tell us about the kinetics here? What's the rate constant base E and the rate constant base 10? All right. So we've got the VOD 8 is 180.9 milligrams per liter, and the ultimate VOD is 212.0 milligrams per liter. We want to know what is K, lowercase k, and what is K, the uppercase K. So For the lowercase k, then that's where we're working with base E, natural log. We start off with the equation of that the BOD at some time is the ultimate BOD 1 minus e to the negative kt. Okay, we can rearrange that to solve for the k value. We'll get BOD at time t divided by L naught. That'll give us 1 minus e to the negative kt. And then I'm going to have to move this down. That gives us e to the minus kt is 1 minus BOD sub t divided by L naught. Okay, so the way that we're going to do this is take the logarithm of both sides now, and then that leads to kt is equal to negative ln 1 minus BOD t divided by L naught. And finally, k is negative logarithm 1 minus BOD t divided by L, and all of this divided by t. So we'll substitute in some values now. So negative logarithm 1 minus our BOD at the end of 8 days was 180.9 milligrams per liter, and the ultimate BOD was 212, and then all of that is, the T was 8 days. So the K value that we'll get when we pop those numbers into the calculator is 0.24 inverse days. Day to the minus 1 is the units of the K value. All right. So if we want to know the base 10 K value, we're told that it is lowercase k divided by 2.303. So that's 0.1042 inverse days when that's base 10. So that's how you can characterize the kinetics, is if you know the concentration at 2 different times, it doesn't have to be ultimate and BOD at time 8. It can be any 2 times, then you can find out what is the rate constant K. Any questions about that? By the way, I just thought of it. I was real impressed that nobody groaned and rolled their eyes when I said you guys had to do presentations in 2 weeks. If this was an undergraduate class and I said you guys have to do presentations, it would be like, you know, a bunch of moaning, and I can tell the maturity level here is much higher than I'm used to working with my other students. So I appreciate that. Maybe you'll be groaning on the drive home or something, but at least you held it together in class. All right. So that said, in the lab, I already told you that the way a BOD test happens is that you take a little bit of wastewater, only a little, and put it into a bottle. Usually these bottles are 300 milliliters. For some reason, that's just the standard. And it's a glass stoppered bottle that is airtight. Why do you suppose it's important for this bottle to be airtight when you're doing the BOD test? Exactly, yeah. You want it to be a closed environment. You don't want additional oxygen seeping in, because then you wouldn't know how much came in, and so obvious reasons there. It's usually incubated in the dark at a fixed temperature. We actually have a special refrigerator back in the lab that it has both heating elements and refrigeration built in, and you can dial it to any temperature and it'll keep it within 1 degree of whatever temperature you'd like it to be at. You measure the dissolved oxygen of the water at the end, to compare to the initial, and the BOD, the demand, is just the initial minus the final. Usually though, you're using a waste that's so concentrated that you wouldn't be able to measure all of the demand, because a wastewater, if it has 180 milligrams per liter of demand, it's going to exhaust all of the dissolved oxygen before it reaches its ultimate demand, and so there will be dilution. And I think in the homework set that I've given you is a very simple BOD test problem you need to do, and in that case the dilution ratio is the total bottle volume, which in most cases is 300 milliliters, and then the sample volume, that's the amount of wastewater that was added, and that's how you can find the dilution ratio. One thing is that not all wastewaters have bacteria in them to begin with. Remember, we were talking about sugar and how sugar isn't a pollutant, but if you add it to the river, the bacteria that are naturally in the river will start to grow. Well, if we did that test in a VOD bottle, if we just added a sugar cube and we poured in distilled water that had dissolved oxygen in it and stopped it up, the sugar would stay there and the concentration of oxygen wouldn't go down, because we're missing something. We're missing the bacteria. And so sometimes in a waste, if there's no bacteria to begin with, they have to seed the bacteria. And so the calculations are a little bit more difficult for calculating what is the BOD when you've actually seeded bacteria into the sample. I just want to show you what that looks like. You won't need it for the calculations you're doing on the homework, but what I wanted to point out is that you have to keep track of the initial and final dissolved oxygen concentration of two different things when you're doing a seeded bottle test. You have to find out how does the concentration change of the water that you use to add some bacteria, and then also you're keeping track of the test itself. And so in the bottle, if it's a seeded test, you would have the wastewater, some dilution water, and some seeding water. So there would be, in a seeded BOD test, there would be 3 different liquids inside of that bottle. And to find out what's the BOD of the waste, you have to track the change in dissolved oxygen of the seeding water and the sample itself. So there's the equation for that. Now you've seen it and you know that such a thing exists and is out there. There are some special considerations when you're doing a BOD test. A 3 or 5 day test will reveal most of the demand, but it's not going to show all of the demand. And we've already talked about how there's an ultimate demand that's different and sometimes quite a bit higher than the 3 or 5 day test. Another thing is that the rate constant can vary depending on where the wastewater is coming from. Some waste are very high in strength. Industrial waste sometimes will have a high BOD but not very many bacteria in it, and so how quickly it reaches its ultimate demand can vary from waste to waste. And so let's just look at a difference between a municipal wastewater and industrial wastewater. Now, if you did a BOD test for 5 days, it would look like these two wastewaters have the same oxygen demand, because over the course of 5 days they both have 200 milligrams per liter. But that would be deceptive, because you'll notice that the ultimate BOD of the municipal wastewater, it plateaus out at 243, but then the industrial wastewater goes so much higher. It eventually gets all the way to 457. So, if the industrial wastewater has so much more BOD, then why was it that it looked like they had the same demand? And the reason why is the rate constant, the K value. The municipal wastewater was achieving its ultimate BOD much more quickly, because there was either the energy source was easier to utilize, like it was a simpler carbohydrate, compared to the industrial wastewater. The bacteria can't break it down as quickly, and that's why the K value is lower in the case of the industrial wastewater. Another kind of interesting thing that you have to sort of be aware of when you're interpreting a BOD test is the effect of temperature on how quickly it reaches certain levels. And so in this case, the two different wastes are broken down at different temperatures. They have the same ultimate VOD, but in 5 days, the one that is colder, the 10 degrees Celsius water, when the water is cold, it has a lower K value because the bacteria are sluggish. They're not eating very quickly because it's so cold. The cellular respiration is depressed in a cold temperature. And so in 5 days, maybe they only can break down 21 milligrams per liter, but in warmer water, they would more quickly reach that ultimate VOD. So just a couple of considerations in interpreting the results. Another term that we'll come across during the semester is chemical oxygen demand. Now, so far we've been talking about biochemical oxygen demand, meaning just the bacteria are using oxygen. Well, there's also going to be some things in the wastewater that maybe the bacteria aren't breaking down, but a reaction to dispose of that other waste would still demand oxygen. So gasoline is an example of, if you have gasoline dissolved in water, bacteria aren't usually, there may be some exotic bacteria that could use a little bit of gasoline for respiration, but in general, there isn't going to be a lot of biochemical oxygen demand for gasoline mixed into water, but there would be a chemical oxygen demand if you're doing a chemical reaction to break down that gasoline in the water. It has the same units as VOD, milligrams of oxygen per liter of the waste. One of the constituents of wastewater is to understand the solids content that is in wastewater. And I already talked about clay being dissolved, well, not dissolved, but being suspended in water. Clay is fixed, meaning that if you put clay in an oven, it's not going to burn away. But if you put volatile solids in the oven, like algae, if there was algae that was growing in the water, and you evaporate all the water away, and then you are left with some solids, but the solids were organic material like algae, then if you burn that solid material at 550 Celsius, then the volatile solids will go into gases, and so if you're measuring the before and the after, the volatile solids would be gone. Okay, so suspended solids has two subsets. There's volatile and fixed. So fixed and volatile together. If you add them together, that is the suspended solids. And dissolved solids is something entirely different. It is the salts that would pass through a filter if you were trying to filter a wastewater. So settlable solids is those fraction of the suspended solids and the volatile solids that are big enough and have a high enough density that over time they'd settle out of the water. When we are talking about the strength of sewage, how concentrated it is, the solids and VOD, what we've just been talking about, those are the two parameters that are most relevant for design. You know, picking out the sludge recirculator and the aeration basin. It's the VOD and suspended solids that are the primary design factors. So here's an idea of the concentration of these different constituents in wastewater. Typical, like a medium strength wastewater, would have a VOD of around 220 milligrams per liter. Typically, it might have suspended solids of, they're saying here, 220 milligrams per liter would be a typical concentration. You can see some of the other pollutants that are really important would be the nitrogen, which is a nutrient that stimulates the growth of algae and problematic weeds. Phosphorus is another nutrient that's considered waste. Now, alkalinity isn't a waste, it's just a characteristic of the water. Grease definitely can be a problem. It can cause a lot of trouble when it gets into the wastewater treatment plant. because it's difficult to remove. And so with grease, the focus is really on prevention and pre-treatment rather than trying to remove it if it gets to the plant. We talked earlier today about a flow equalization basin. And here is a diagram of some typical temporal variations of not only the flow rate over time, but what you also notice is that BOD and suspended solids concentration vary over time. Okay, so we already talked about this line, the solid line. And we talked about how there's a bump at night because everyone came home from work and they're washing dishes now. And in the middle of the night, we talked about how it's low because people are asleep and they're not using water. But why is it you suppose that BOD varies over time? What accounts for that? What do you mean? Uh-huh. All right. Right. Okay, very good. And the most extreme example of that is consider the middle of the night. You know, a lot of the water in the sewer during the middle of the night is actually due to cracks in the pipe. They call that infiltration and inflow. If there is water that's seeping down into the sewer pipes because it's raining, or if there's a crack in the pipe, or if the pipe isn't jointed together properly, that I and I. So at 4 a.m., a lot of this flow is just because it's groundwater or surface water that's getting in. Maybe it's not from flush toilets or showers, it's just really, it's fresh water. And so it makes sense that the BOD is going to be pretty low in the middle of the night because a lot of the water that's running through the sewer isn't contaminated. But then during the day, you know, it's more deliberate discharge. A greater fraction of what's in the sewer is going to be from people flushing their toilets. So, and food particles. You know, the food scraps that get grinded up in an garbage disposal and, you know, washed down into the sewer, that increases the BOD a lot. And the same thing is true of suspended solids. It's just in the middle of the night, less of the waste water is intentionally flushed, and during the day more of it is. So that talks about the temporal variation, not only of the quantity, but in the strength of the waste. There are seasonal variations too. Just because you have this pattern that we're looking at here, this is the pattern maybe in January, it's not necessarily going to be the same pattern in July because the way people use water changes during the season. And this is showing in Chicago 3 interesting things. The first at the top there is rainfall. And so it shows in Chicago they get the most rain in June. And part of the reason why that's shown is that if you have a lot of flow during the rainy season, it tells you that your pipe network is suffering from a lot of infiltration and inflow. If you got a lot of water in the sewer when it rains, that's a bad sign. It means you've got problems. There shouldn't be a tight correlation. There will always be some, especially in Huntington and other places that has a combined sewer. Well, anyways, so this next line is the BOD. And so it's showing, for example, you can see spring thaw is written here. When there's runoff from snow melting, that gets into the sewer, then that's going to bring down the relative strength of the BOD. So this is a ratio on this middle graph. It's the ratio of the average monthly BOD to the 5-year average BOD. So they're showing that in the fall, there is a much higher concentration of BOD than the sort of annual average. And then finally, this is the flow rate variation over the seasons. So it looks like in the spring when the snow is melting, that's when they have the most flow rate in the pipes, and in the fall is when the flow rates are the lowest. So here's another illustration of seasonal variation, in this case Modesto, California. And what's interesting about Modesto is it's in the Central Valley of California where There's a lot of vegetables that get grown in the Central Valley, and when they're harvested, in many cases what they'll do is they'll can them. And so food processing in the Central Valley is a really big source of waste. And so if you look at when is the peak here, for the seasonal peak in Modesto, the BOD it's really a huge change. So the BOD is the dashed line. All of a sudden it peaks in the fall. So here's 6, which is June. Here's 1, which is January. So it looks like it's towards the end of the growing season that the BOD goes up. And so there's a good chance that these spikes in BOD have to do with the food processing plants coming online during the summer and fall harvest of vegetables. So, you know, the take-home message is that every place is unique. You may have some special factory or some special characteristics that changes the strength and timing of the waste, and it's really important to do a study of what is the strength of the wastewater, what is the characteristics. Before you begin thinking about the treatment plant, you have to understand what it is that's being treated. So here's an overview of a typical wastewater treatment plant. And so the water that comes in, first of all, goes through a screen, and that's to remove you know, rags that get flushed down the toilet. And people put all sorts of things down the drain, and sometimes if you have street level catch basins that are also going into a combined sewer, then it just gets even crazier from there. You're getting baseballs and wedding rings and big wads of money, stuff like that. So I have heard that, especially like in drug-prone areas where people are flushing drugs down the toilet and money, that you never know. You work the bar rack, you could get rich, right? But it's also really, I've been to a lot of wastewater treatment plants, and by far the one that smells the worst is the bar screen. You don't want to be in the bar screen area. It's just awful. Okay, so it removes the biggest fragments. Then the grit chamber is removing sand and particles that settle out easy. And the reason why it's important to remove grit is that if it stays in the water, then it can erode pumps. It can cause pitting and damage to the impellers and to the pipes that are in a treatment plant. So you're just removing it because it's abrasive, really. The primary clarifier is before you get into the real magic of the wastewater treatment plant. In the primary clarifier, you're removing what will settle and what will float. You know, you're maybe removing about 30% of the BOD through primary clarifiers. It's only going to remove not what's the dissolved BOD, but it's removing the BOD that is still in floating and settling ability. And I'll let your imagination do the work of what that is going to be. You know, like foam and grease will be removed off the top. Okay, so here's where the magic happens. 4 and 5 is recirculated sludge off the bottom of the secondary clarifier being re-injected into the aeration basin, which is number 4. And activated sludge was discovered and started being used in the 1900s. Before that, nobody had the idea that if you introduce the sludge, the reason for that, why it's a good thing, is that the sludge that accumulates in the secondary clarifier, by the time you pump it back into the aeration basin, those bacteria are hungry, and they are really going to go after the dissolved BOD that's in the aeration basin. And you're adding air for the reasons that we talked about earlier, is that, you know, bacteria, when they're eating food, they also need air. And so the food that they're eating is this BOD that you don't want to get into the river. So they're consuming it in a certain spot that you set aside as this location where you want to be a lot of consumption of the BOD. So that's the aeration basin being fed this hungry bacteria from the secondary clarifier. Some of the sludge, though, you have to waste. And 7, the sludge digester, is where you break down the sludge that's being generated from the primary clarifier and also the wasted sludge from the activated system. Just breaking it down and dewatering it before you maybe bury sludge, or some places they burn it Other places they turn it into compost and use it for fertilizer. But the water that comes out of the secondary clarifier actually looks great. If you've been to a wastewater treatment plant, sometimes they'll do things like they'll take water out of their secondary clarifier and they'll have it in a fish tank just to show that how clear it is. You know, looking at it, you wouldn't know that it was necessarily wastewater. There's still a little bit of BOD, kind of like a typical discharge limit maybe would be 25 milligrams per liter of BOD, compared to what came in was 200, maybe 300 milligrams per liter of BOD. 6, which is disinfection. Some places don't bother disinfecting in the winter. Like in Indiana, which is where I did my graduate school, they didn't disinfect there during the winter because they figured nobody was going to be out swimming in the river in January. So why bother chlorinating the wastewater if nobody's going to be coming into contact with it? It might be, instead of chlorination, it might be UV disinfection. Increasingly, UV irradiation is being used to disinfect. But if we just take a step back and think about what's the main point of this whole process, mainly to remove solids, BOD, neutralize the pathogens that are in there so that it doesn't cause any harm to people. In addition to the processes that are shown here, we can also remove, if we're really careful about how long the bacteria spend inside of the aeration basin, we can also remove nitrogen pretty effectively in wastewater treatment plants. And there are some tertiary processes like filtering or nanofiltration and membranes that can make the water even cleaner and more suitable for reuse. All right. I think we already talked through most of this on the previous slide. So this class, just to remind you, is talking about biological treatment of wastewater. And so we'll just touch on the whole process briefly because it's hard to jump into just the biological aspects of it without setting the foundation of the other steps. I mean, for the most part, this semester, we're going to focus on 4 and 5 and a little bit of sludge treatment. But, I mean, the majority of the course is understanding the biology of activated sludge. But before we can do that, we will talk about the clarifier and the grit chamber and so on. And so the driving force, whether it be an energy source or a reaction that's causing the reduction in the pollutants, it's the biological treatment in the aeration basin that we'll focus on for the most part. But the way you remove grit and settling is just the effects of gravity. Disinfection is a chemical process. We'll touch on disinfection briefly at the end of the semester, but for the most part, it's biochemical processes that's in this course. And finally, here's just a slide that shows some of the typical treatment efficiencies for different steps in the treatment process. What we were looking at in this overview is activated sludge, which is by far the most common form of secondary treatment. But we will actually talk about something that's called trickling filters. It's an attached growth biological treatment rather than suspended growth. And I actually love attached growth. I think it's really interesting. In suspended growth, you've got just the bacteria floating around in the tank and they're floating around in the wastewater that's being treated. But in a trickling filter or other kinds of attached growth, what you've got is you're pouring the water over a colony of bacteria and they're eating the BOD as you do that. So that's an overview of where we're headed. Any questions? We used the full time this week. Sometimes we will, sometimes we won't. But let's just take one final look at these announcements and refresh our memories where we're headed. You've got a homework assignment due next Tuesday, homework 1. So send me emails if you have questions on the homework, or if you have a problem, you can stop by during my office hours. Whatever's best for you, I'll do my best to help you out. And then in 2 weeks, we'll use the most of our class time will be used for the presentations that you're going to do.
Any particular way you want us to address the presentation?
No.
Whatever.
You know, I want you to dress with a crazy hat. No, just whatever you want. I know Professor Huffman likes you guys to dress up, but I'm not so picky as that. All right. All right, thanks, guys. Have a good one.